Hello everyone, this is Jayashri from 3rd year IT department of GRIT. I'm here to present a mini project which I worked on along with my teammates Pranati and Prabandha under the guidance of Dr. CH Vidyadhari. The title of our project is Driver's Drowsiness Detection System. Coming to the abstract, drowsy driving is one of the major cause of road accidents and deaths. Truck drivers who drive for long distances, bus and car drivers who drive for long hours are prone to such accidents. There are few conventional methods like ECG, EOG, which are either vehicle based or physiological based. Few methods require expensive sensors and data handling. So, a real time driver's drowsiness detection system, which is behavioral based, is required. In our developed system, a webcam records the video and driver's face is detected using image processing. The eye aspect ratio is computed and depending on its values, drowsiness is detected and an alarm is activated to alert the driver. In the existing system, most of the methods are either vehicle based or physiological based. The vehicle based comprises of turns of steering, braking, velocity, and degree of deviation, which are less efficient. In physiological based, we use few medical techniques like ECG, EOG, EEG to detect driver's heartbeat and pulse rate to determine the level of drowsiness. These methods are intrusive and distract drivers. So, behavioral based driver's drowsiness detection is required, which analyzes driver's visual behavior such as eye aspect ratio, closing, yawning with the help of single webcam. So, our proposed system consists of a camera placed in front of driver which detects drowsiness using a webcam. By using our project, we record the driver's video and driver's face is detected and classified using CNN. Facial landmarks are detected and eye aspect ratio is computed and depending on its values, drowsiness is detected and an alarm is activated to alert the driver.
These are the UML diagrams for our project. In the activity diagram, the system starts by capturing an image from a camera focused on the driver's face. In the next step, the system processes the captured image to detect the presence of a face. If a face is detected, a region of interest is created around the face. If the face is not detected, the monitoring continues and captures the next image. Within the detected face region of interest, the system attempts to locate the eyes. Upon detection of eyes, it feeds it to the classifier, or else it continues monitoring and captures the next image. The detected eyes are processed by a classifier, which is a machine learning model trained to distinguish between open and closed eyes. If the eyes are open, it continues monitoring and captures the next image. But if the eyes are closed, a score is calculated to check the drowsiness. The system calculates a drowsiness score based on the duration and frequency of the driver's eyes being closed. If the score indicates drowsiness, it triggers an alert to warn the driver, or else it simply continues monitoring and captures the next image. The triggered alert is issued to the driver, which is an audible alarm. In this way, the system continues to monitor the driver and detect drowsiness. Coming to the sequence diagram, it begins with the user, who in our case is the driver being monitored by the system. The camera takes an image of the driver and then the captured image is sent to the face detection system. The face detection system processes the image to detect the face within it. If a face is detected, the system creates a region of interest around the face, and the region of interest is sent back as part of the image to the main system. The image with the region of interest is sent to the eye detection system, and the system processes the region of interest to detect the eyes within the face. The detected eyes are then fed to the classifier. The classifier receives the eye data and categorizes the eyes as either open or closed. This categorization is then sent back to the eye detection system, and the main system calculates the drowsiness score based on the categorization received. The calculated drowsiness score is written to the main system, which can decide whether to alert the driver based on the score. If the drowsiness score indicates drowsiness, an alert is triggered for the user, who in this case is the driver. This is the component diagram, and the first component here is the camera, which captures images of the driver. The captured image is sent to the face detector component. The face detector detects the face within the captured image and defines a region of interest around the face. The detected face and region of interest are sent to the next component, which is the eye detector. The eye detector component detects the eyes within the face region. The detected eyes are sent to the classifier component. The classifier performs two main tasks. First is the classification of eye state, in which it classifies whether the eyes are open or closed. The second task is to calculate drowsiness score. Based on the eye state over a period of time, it calculates a drowsiness score. The classification results and drowsiness score are sent to the drowsiness detector component. Drowsiness detector uses the drowsiness score to determine if the driver is drowsy. If the driver is detected to be drowsy, the system can trigger alerts or take proper actions. This is the system architecture. The video is first divided into frames using OpenCV. Hard Cascade takes these independent frames and detects the face. The CNN algorithm mainly performs the two tasks of feature extraction and classification. It extracts the eyes from the detected face and the eye aspect ratio is calculated. From this score, the model determines if the eye is open or closed. The eye aspect ratio is calculated over consecutive frames, and if this ratio is below the threshold for a specified number of frames, the driver is classified as drowsy. Upon this classification, an alarm is activated to notify the driver of the drowsy state.
Coming to the implementation of our project, we have divided our project into three parts: data preparation, model training, and main part. In data preparation, we have separated our dataset into training and testing sets using SHUtil and TQDM libraries. These training and testing sets are further divided into open, ice, and closed as datasets. In model training, we have trained a model with two main libraries, TensorFlow and Keras, and from these libraries we have imported Inception v3, which is a pre-trained CNN model available from Keras application used for image classification tasks, and model allows us to create a custom neural network architecture by specifying input and output layers, and all these dropout, input, flatten, dense, max, polling are the utilities from Keras used for model architecture, and image data generator enables real-time data augmentation and batch processing of image data during training process. And we have given our batch size 8, which indicates that 8 images will be processed together in each batch during training and testing phases. Later, we have done with training and testing of our model. And coming to the model summary, as we are using CNN, first I have flattened the model. Later, for fully connected layers, I have used ReLU activation function with 64 neurons and softmax activation function with 2 neurons. Later I have loaded the model summary, and after loading the model summary, next step, we are saving the best model based on validation losses using model checkpoints, and I have given 5 epochs to my model. Coming to the main process, in main process I have imported OpenCV, which is used to divide video into frames, and I have imported load model from Kensar and Keras application to load the previous trained models, and NumPy for numerical computations, OS for interacting with my operating system, and Mixture is a library of Pygame which is used for multimedia tasks, and image data generator for image processing. And for detecting the driver's face and eyes more clearly, I have used Har Cascade. And coming to the main process takes the driver face as input and it calculates the I score. If the I score exceeds 15, it activates alarm, and it stops the alarm only if the confidence is greater than 0.90. Our model has the best accuracy with accuracy is 94% with the loss of 14%. Coming to the final results of our project, the alarm rings when the driver closes his eyes. And it stops when the driver opens his eyes widely. Finally, I want to conclude the video by thanking our project guide Dr. C.H. Vidyadhari, who is Associate Professor in Gogaraja Rangaraju Institute of Engineering and Technology. Thank you.